Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 4.2.4, which is Trigonometric Applications. We're going to begin with 4-89, Climbing in Yosemite. It says, David and Emily are climbing El Capitan, a big cliff wall in Yosemite National Park. David is holding a rope attached to a carabiner, which is a rope pulley that is on the wall, above Emily as she climbs. When Emily stops to rest, David wonders how high she has climbed. The rope is attached to his waist about 3 feet above the ground, and he has let out 48 feet of rope, which goes to the carabiner and then back down on the wall to Emily's harness. The rope at David's waist makes a 55-degree angle with the ground, and he is standing 20 feet away from the base of the wall. So, for those of you who remember the UFO problem or the seagull churro stealing problem with all of those involving tangent, you guys will recognize this problem, except now that we're learning sine and cosine, we just have to be ready to enter those into the fray because they might play a role. And so from here, this is what the diagram should look like. The rope pulley is going out of David's waist right there. And so from here, we have to also keep in mind that David is 3 feet off the ground. So whatever we have here, we're going to have to add 3 to that distance if we end up having to figure out how far off the ground Emily is, which looks like Part B is asking us to do. Well, we know that the rope at David's waist makes a 55-degree angle with the ground. He's also standing 20 feet away from the wall. And they want us to find how far away the rope, or how long the rope is. It says assuming that the rope is pulled tight, how long is the rope between David and the carabiner? So the carabiner is right here. And so I'm going to go and find out this distance. I'm going to go and call that R. Usually I call the hypotenuse of a right triangle R. It's just my choice. It's up to you. So from here, I've got an angle. I've got an adjacent side. I've got a hypotenuse. To me, the most obvious relationship is to use cosine. So I'm going to say cosine of 55 degrees is going to be equal to 20 over R. I'm going to multiply the R on both sides. I have R times cosine of 55 equals 20. And then I'll go and divide both sides by cosine of 55. And that's going to get me R equals 34.87 feet. Okay, that is how long this blue distance is right here. That's how long that blue distance is. This is 34.87. I apologize for that interruption right there. I had a mosquito buzzing around my ear, and if you've ever heard that sensation, the sound is quite annoying, but I believe that mosquito is now dead. So, okay, let's keep on going. In part B, it says, how high up the wall has Emily climbed? And we have to describe our method. Okay, this is actually quite involved. I'm going to go and put Emily right here, because that's what it kind of looks like. It looks like there's a little bit of a gap right here. And I'm going to do a couple of different things here. I'm going to go and find out the length of that purple space right there. How do I do that? Well, I know that David has extended 48 feet of rope in total. And because 34.87 of that rope is being occupied by the blue, I know that whatever's left in purple is going to be what's left of that 48 feet of rope. So I'm going to go ahead and do 48 minus 34.87. And what that gives me, it gives me 13.13 feet. So that's how much this purple space is worth. Now what I'm going to do is I'm going to go and find out the total distance of this orange space right here. So what I'm going to do is I'm going to go and find the total distance of the orange space. How do I do that? Well, I'm going to go and call him Y. And I have to remember that whatever I find for Y, I'm going to have to add 3 to it because the rope is attached at David's waist, which is 3 feet off the ground. So in order to find this Y, I'm going to go and say, well, tangent of 55, and I chose tangent because that is the ratio of opposite to adjacent. Now I could have used sine if I wanted to. The problem with using sine is that because 34.87 is a decimal and there were many more numbers after that, I figured I would use 20 because that's my real locked-in number. So the tangent's going to give me my more accurate version of what y is supposed to be. So opposite over adjacent right here. And I'm going to go and multiply 20 on either side. And what I have is 20 times tangent of 55 is equal to y. And then I got to remember, I got to add that 3 to it. This is exactly like the 6-foot woman seeing the UFO. And so what I'm going to do is I'm going to go and find out the value of this. And right here, this is going to be 28.56, and I'm going to add 3 to it. So what I get is I get 31.56, equaling the total value of y right here, right? And so for me to call it y is actually kind of misleading here. So I'll just go and replace this whole thing, and I'll replace this whole thing here with 31.56. So what I'm going to do is, in order to find out how high up Emily is off the ground, which is going to be now this thing here in green, green, I'm going to take my total, my large side, and I'm going to subtract my short side. So what I have is I'm going to do 31.56 minus 13.13. And that is going to get me 18.43 feet off the ground. Okay, that should wrap up B right there. So again, kind of an involved problem right there because you had to find out the length of the short space, which is what Emily is dangling from, and then find out the total space, which is using tangent plus 3 because of the distance between David's waist and the ground, and then subtract the two values to get the distance of the green, which is the space between Emily and the ground. So hopefully that made enough sense. I will be back with the next problem. In 4-90, they talk about the Bungling Brothers Circus is in town, and you were invited as part of the crew to set up the enormous tent. It says the center that holds up the tent is 70 feet tall. So let's go and draw this pole here. This is 70. It says to keep it upright, a support cable needs to be attached to the ground. It needs to be attached to the top of the pole so that it forms a 60-degree angle with the ground. So here we go. This is going to be 60, and here's the ground. Here is 60. And they're asking you how long is the cable. So I feel like they're asking you for R. And then in B, I'll go and just fast forward a little bit. It says, how far from the pole should the cable be attached to the ground? It looks like they're asking us to solve for X. So let's go and take care of these one at a time. This one's a lot more straightforward than the Emily dangling from the mountain problem. So what I'm going to do is I'm going to go and use a trig function to solve for R first. And so from here, I've got an angle opposite hypotenuse. That sounds to me like sine. So sine of 60 is going to be equal to 70 over R. I'll go and multiply both sides by R. So R times sine 60 is equal to 70. Divide both sides by sine 60. So what I get is R equals 70 over sine 60. And what you end up getting for R is 80.83 feet. And that takes care of A. To take care of B, how far should the pole be from the ground? Well, again, we could use cosine if we wanted to and go adjacent over hypotenuse. Again, kind of like the Emily problem, I would rather not use a decimal answer that I already have because this 8.3 is certainly not where that decimal ends. And in order to get the most accurate version possible, you want to make sure you use the values that are already given to you, especially when it's a clean number like 70. So when that happens, I am more inclined to use tangent because tangent will get me opposite over adjacent. So what I have is tangent of 60 is equal to 70 over x. So it seems like we're kind of back in old territory here. So x tan 60 equals 70. So x is equal to 70 over tan 60. And when we bust that into the calculator, we get 40.41 feet. So again, the biggest takeaway from this problem is make sure that we do not use a value that we already have. It could lead to a rounding error. It's just a place we don't want to be. So I'll be back with the Next problem. And in this problem here, it says Nathan is standing in a meadow exactly 185 feet from the base of El Capitan. At 11 a.m., he observes Emily climb up the wall and determines that his angle of sight up to Emily is about 10 degrees. And we can use Desmos to visualize the problem. It's not a big deal. We can just draw it out. In part A, it says, if Nathan's eyes are about 6 feet above ground, how high is Emily at 11 a.m.? So we're looking at Nathan here. And here's Emily at the top of this triangle. Here's Emily right here. And so remember, he's standing 185 feet away. And remember, whatever my answer is, if I'm trying to find out how high Emily is, I'm only solving for this part of the triangle here. This is y. Whatever I get for y, I'm going to have to add 6 to it. So from here, at 11 a.m., he observes Emily up the wall, and his sight elevation is 10 degrees. So from here, I feel like that's a classic tangent problem. So I can say here for part A that tangent of 10 degrees is equal to y over 185. So go and just multiply the 185 over. 185 over. So 185 times tangent of 10 is equal to y. Now, here's the thing, is I'm going to get a number for that, but I also need to add 6 to that value. So her height, when all is said and done, is going to be 185 times tangent of 10 plus 6. That ends up becoming 38.62 feet in the air. That's how high Emily is at that moment in time. So pretty classic problem. We've dealt with this before with the woman in the UFO and the guy staring at the Tokyo Skytree. We've been through those problems before, and so hopefully that makes enough sense. In part B, it says, at 11:30 a.m., Emily has climbed some more, and Nathan's angle of sight is now 25 degrees. How far has Emily climbed in the past 30 minutes? And so we know that her current height is 38.62. If I can just find her height when the angle is 25 and I subtract 38.62 from it, then I think I'll have her total distance changed in 30 minutes. So here's Nathan again. Here's Emily a little bit higher. Still 6 feet off the ground. Still 6 feet off the ground. Now the angle of sight is 25 degrees. And he's still standing 185 feet from the mountain. So I'll go and call this y sub 2. And I'll say that tangent of 25 is equal to y sub 2 over 185. Again, same thing that we've always done. I'm going to multiply 185 over, and I get 185 times tangent of 25 equaling y sub 2. So if I punch that into the calculator, if I tangent of 25 times 185, and I add 2 to it, or rather add 6 to it, I'm going to get my new height. I'm going to get my new height to be 92.26 feet. So if I take my new height and I subtract my original height, I should end up with the total distance changed. So let's see what that looks like. 92.26 minus 38.62. So if I subtract 38.62 from this answer, I end up with 53.64 feet changed. So it looks like Emily climbed 53.64 feet more in the air. Okay, let's take a look at part C. I am running out of space. I'm going to have to clear the board. Give me 1 second, please. So in part C, they're telling us that Emily has climbed 32 more feet in 10 minutes. And we're going to find out the angle that Nathan will have to look in order to see her. So this is going to involve some inverse trig here. So at this point in time, Emily has climbed 86.27 feet in the air. Nathan is right here. We're trying to find out the angle at which Nathan's going to have to look. So we know that tangent of theta is going to equal 86.27, but we're going to add 32 more feet to it. Nathan's distance from the mountain has not changed. He's not moving, so that's going to divide by 185. And so what I get is I get tangent of theta equaling 118.27 divided by 185. And I got to solve for that theta. Again, I'm not going to divide both sides by tangent. I'm going to take tan inverse on either side. So theta is going to equal 118.27 over 185, and that's being tan inversed. So as a decimal, that ends up becoming 32.59 degrees. So Nathan will have to look up at an angle of 32.59 degrees to continue to see Emily. So, bottom line, trig applications. It's just like the tangent problems. It's just like the seagull stealing the churro problem or the guy looking at the Tokyo Skytree, but now they're involving some more trig operations. Cosine, sine, tan inverse, cos inverse, finding angles. So hopefully you found this useful. I will see you all in the next episode, and as always, please leave questions or comments in the comments area. See ya.